Good day and welcome back for the fourth part of our discussion on trigonometric substitutions. So trig substitutions are a technique of integration that we would want to apply based upon two factors. One, if we could evaluate the integral using previous methods such as substitution or integration by parts, we would probably want to do so. But if not, and the integrand contains expressions of the form that we see in the left column of our table, that prompts an associated trig substitution, and then we use an associated identity to simplify the integrand. We've gone through multiple examples illustrating the process we would use for trig substitutions on an indefinite integral. So to continue our discussion on, we will cover two more examples in this video. One, using a trig substitution to evaluate a definite integral, and then a second example where we have to do some algebraic manipulation to get it to the point of where we can use a trig substitution. So let's go ahead and jump into this definite integral. This is not something our previous techniques of integration will apply to. There's no obvious substitution. Integration by parts doesn't seem reasonable. But note, this expression x squared minus 1 is telling us to consider a trig substitution. So this is a case where a is equal to 1 and it's x equals secant of theta. And if x is secant, dx would be secant theta tangent theta d theta. And our goal is to take this integral that only involves the variable x and rewrite it now so that it only involves the variable theta. So x squared is going to become secant squared theta. The x in the denominator is secant theta. And the dx is secant theta tangent theta d theta. And note in this case the secant thetas immediately cancel. But before going any further, I'm going to note a definite integral with a substitution requires us to change our limits of integration. In the original integral, our limits are going from x equals 1 to x equals 2. In this new integral, we need our limits of integration in terms of our variable theta. And we can always do that using our substitution. So in this case, when x is equal to 1, our lower limit of integration, we would have 1 equals secant of theta. And we need to determine or solve for theta. And as we've mentioned previously, it's oftentimes simpler to work in terms of cosines than it is in terms of secants. So secant is 1 over cosine. We would like to know where is cosine equal to 1. And that happens when theta is equal to 0. Our lower limit of integration is 0. For our upper limit of integration, we start off in terms of x values at 2. So we need to know what is our value of theta where secant is equal to 2. Well, secant of theta equals 2 means 1/2 would be cosine of theta, which is the common value pi over 3. So our upper limit of integration is pi over 3. And note, we started off with a definite integral only involving x. We've expressed it in terms of a definite integral only involving theta. In this case, once we evaluate this definite integral, we get back a number, and we are done. Because we've gone through the trouble to convert everything in terms of theta, once we evaluate, we are done, no resubstitution necessary. So let's go ahead and evaluate. Note, underneath the square root, the secant squared theta minus 1 is tangent squared theta. So we have the integral from 0 to pi over 3 of the square root of tangent squared times tangent. The square root of tangent squared is tangent, so we really have the integral from 0 to pi over 3 of tangent times tangent, which is tangent squared. which is a very familiar trigonometric integral. In fact, we evaluated this several times recently. So instead of going through the details, I will let you fill them in. But rewriting tangent squared as secant squared theta minus 1, anti-differentiating term by term, we get the antiderivative is tangent theta minus theta, and it's a definite integral. So we evaluate from 0 to pi over 3. Replace each theta with a pi over 3, minus sign, replace each tangent with a 0. And recall, we always must take it further when we have trig functions at common angles, which 0 and pi over 3 most certainly are. Tangent of 0 is 0, so that entire second piece goes away. In terms of tangent of pi over 3, that's not something I expect us to just maybe know immediately, but we remember, tangent is sine over cosine. So it would be sine of pi over 3 divided by cosine of pi over 3. And you could leave it in this form, but note when we have fractions over fractions, it's maybe more convenient to cancel off those 2's and write it in this simpler form, root 3 minus pi over 3. So from a big picture perspective, when we are using a trig substitution to evaluate a definite integral, our approach is nearly identical. The only difference takes place in terms of the limits of integration. But once we get those limits of integration converted in terms of thetas, we simply evaluate the definite integral. So moving on to our second example, let's evaluate the indefinite integral of the square root of the quantity 5 plus 4x minus x squared. And the real difficulty here is getting this started. Upon first glance, it's not even clear what method or technique of integration we would want to use. Of course, you have a sneaking suspicion since we are discussing trig substitutions today. But going through our mental thought process, it does not appear at all that a direct substitution would work, in the sense that there's no obvious substitution to make. This does not look like it's well suited for integration by parts. It's not a trig integral. The only thing that leaves us with that we've discussed would be a trig substitution. So in a sense, we've eliminated all other possibilities, but it's not really in the form that is indicating or prompting us to make a trig substitution. So what we're going to have to do is work with this quantity underneath the square root and rewrite it algebraically. So if I write that with descending order in terms of the powers of x, minus x squared plus 4x plus 5. What I would like us to do is rewrite this by completing the square. And I do realize that it probably seems like it's been a while since we've completed the square. So what we would like to do is somehow write this so that it involves, a number plus or minus some quantity involving x squared. So I would like you to pause the video and see if you can complete the square. And hopefully you've attempted this. The first thing I'm going to do is when we complete the square, we want the coefficient of x squared to be 1. So I'm going to pull a negative out. We'll write this as x squared minus 4x, and then we have our minus 5. So up to this minus sign that's kind of just hanging around out front, what I would like to do is really focus in on this x squared minus 4x. And I would like to write that as x minus something squared. And I will note that there are associated formulas, but I really prefer to think about this intuitively. What number would I have to put here in order for the first two terms when we expand out to be x squared minus 4x? And note, if we had the number 2, if it was x minus 2 quantity squared, that's x squared minus 4x plus 4. But no, the plus 4 doesn't just appear for free. Whatever we add in, we also need to subtract away. So this minus 4 minus 5 is going to result in a minus 9. And now, if we go ahead and distribute the minus sign through, we are going to have a minus 9, so make it a plus 9, and we're subtracting away x minus 2 squared. So we've done some side algebra, which we would describe as completing the square. Now, let's see if this helps us. We've rewritten the quantity in our integrand, which is underneath the square root. This is now 9 minus the quantity, x minus 2 squared. And note, this is actually something that might make us think of doing a trig substitution. Seeing this quantity squared and having 9 minus it, this reminds us of the first type of trig substitution, where we would let this quantity, x minus 2, equal 3 sine of theta. So for a equals 3, because it's 9 squared, we can let x minus 2 be 3 sine of theta. So in that case, if we isolate the x, we would have 2 plus 3 sine theta. So that dx in our integral is going to become 3 cosine theta, d theta. And we can convert from all x's into all thetas. X minus 2 becomes 3 sine theta, and the dx is 3 cosine theta d theta. And I will note that you could do a initial substitution if you do not want to do this all at once. You also could start off and let something like, say, w be x minus 2, and then let w be 3 sine theta. But because we can, I prefer to take care of this all in kind of one step. Now we need to simplify our integrand. And if we look underneath this square root, we have 9 minus 9 sine squared, which is 9 times 1 minus sine squared. So underneath our square root, using the Pythagorean identity, we have 9 cosine squared theta. And when we square root 9 cosine squared theta, it turns into 3 cosine theta. So 3 cosine theta times 3 cosine theta is 9 cosine squared theta. And these integrals of cosine squared or sine squared really have a tendency of appearing. So we want to make sure that we are quick and efficient with those trig integrals. So with that in mind, I think we are in a perfect position for you all to finish up this problem. We've taken care of the new part. What we would now need to do is evaluate this integral and resubstitute. So give yourself 3 or 4 minutes, see if you can do that. So in this case, we will rewrite cosine squared theta as 1/2 the quantity 1 plus cosine 2 theta. I'll pull the 1/2 out of the integral, and then we're left with 1 plus cosine 2 theta inside. And each of these terms we can anti-differentiate individually. Theta plus 1/2 sine of 2 theta. And our final step is going to be somehow rewriting these theta terms so that they only involve x. And looking above, we said x minus 2 is 3 sine theta. So x minus 2 over 3 is sine of theta, which describes a right triangle. Sine is opposite over hypotenuse, which means the length of this bottom leg would be, you guessed it, the square root of 9 minus x minus 2 squared, which comes from the Pythagorean theorem. Unfortunately, we're not quite in the position of being able to use this triangle quite yet because we have a sine of 2 theta. So let's use a trig identity to rewrite this. Recall that sine of 2 theta, this common double angle formula for sine, is 2 sine theta cosine theta. The 2 and the 1/2 cancel. Now working from left to right. Theta can be given in terms of arc sines. Arc sine of x minus 2 over 3 is theta. Plus, we have sine of theta, which is x minus 2 over 3. And then looking at our right triangle, cosine of theta is the square root of 9 minus x minus 2 squared, all over 3. And a common question that I will get, or maybe a mistake that people make, is instead of drawing the triangle to just solve for theta in terms of an inverse trig function and then substitute that in everywhere. That does give you a correct expression representing this indefinite integral, but our goal is to write everything we possibly can without using the inverse trig functions. We can certainly do that for the sine of 2 theta term, but the theta itself, the best we can do is leave that expressed in terms of the inverse sine. So that completes the material for this current video. Now, what remains is one more example that we're just going to set up and get it to the point of where you can evaluate it with a trig substitution, and then an associated class worksheet. So I would strongly encourage you before viewing the next video to locate the class worksheet on Canvas and give yourself a solid 25 or 30 minutes to work through it. These problems in particular have a tendency to be, somewhat lengthy and involved. Because of that, it's also very important to make sure that you're using proper mathematical notation. So find that worksheet, give yourself a solid amount of time to work on it, and then view the next video. So stay tuned and take care.